Good morning, students. Today we will discuss basic theorems of Boolean algebra. Last class I have given the one property. I have solved the first properties of zeros and ones. Again I will rewind from the first. What is this basic theorems of Boolean algebra? You are taking the fundamental laws or postulates of your Boolean algebra. Is used to solve your Boolean theorems. You are going to solve the Boolean theorems with the help of fundamental laws or postulates. So, how are you going to solve this Boolean theorems? By substituting the values of zeros and ones in the place of variable. This technique we call as proof by perfect induction. So, there are four properties of zeros and ones. First property is 0 plus x is equals to x, 1 plus x is equals to 1, 0 into x is equals to 0, 1 into x is equals to x. First one will solve. What is it? You are going to solve using, you are going to prove the theorems. 0 plus x is equals to x. How are you going to prove the theorems? By substituting the values of zeros and ones. So consider this as a LHS and this is a RHS. I am going to substitute if x. For every variable you are going to substitute the zeros and ones. Zeros and ones. Okay. In place of x, first time x is equals to 0. X is equals to 0. Consider your LHS. Consider LHS. What is my LHS? 0 plus x. So in place of x, I am going to substitute with 0. 0 plus 0 is nothing but 0 according to your OR relation. According to your OR relation, 0 plus 0 is nothing but 0. Again, the 0 takes the value of x. So RHS is being proved. You have proved your RHS is been proved. In place of substituting x is equals to 0. If x is equals to 1, consider your LHS. What is my LHS? LHS is nothing but 0 plus x. In place of x, you are going to substitute it as 1. 0 plus 1 is nothing but 1. That is nothing but by according to your OR relation. 0 plus 1 is nothing but 1. 1 holds the value of x. Again, x, that is RHS is being proved. So, for every value of variable, that is zeros and ones, 0 plus x holds the value x. The truth table for it is 0 as it is first column, second x. So, the next one is nothing but 0 plus x. So, 0 as it is in both the condition. One your x value changes, first time 0, second time is 1. Do your OR relation, 0 plus 0 is nothing but 0, 0 plus 1 is nothing but 1. This again holds to a value x and this holds to a value x. So, for every both the values of zeros and ones, 0 plus x is equals to x. So, first properties of 0 plus x is equals to x is being proved. So, second property is 1 plus x is equals to 1. So, this is considered again, this is your LHS and this is your RHS. So, I am considering for first condition, if x is equals to 0, consider your LHS. What is your LHS here? It is 1 plus x. You are going to substitute in the place of x, you are going to put it 0, substituting 0. 1 plus 0, that is nothing but 1. That is your, according to your OR relation. Okay, that is your RHS being proved. Next, if x is equals to 1, consider your LHS, that is 1 plus x. So, in place of x, we are going to substitute this as 1. 1 plus 1 is nothing but 1 according to your OR relation. Again, RHS is being proved. So, for both the values of variable zeros and ones, your RHS is being proved. You consider a truth table. The first column is nothing but 1. Second column is x. The third column is nothing but the result, that is nothing but 1. That is here for 1 as it is. When your x substituting values changes, 1 plus 1 is nothing but 0. That is only exchanges for zeros and 1. Zeros and 1s. Here 1 plus x is equals to 1. That is nothing but my result R. So 1 plus 0 is 1. 1 plus 1 is 1. So your RHS, that is your LHS be equal to your RHS. So for both the values of zeros and ones, your 1 plus 1 is equals to 1. For every value of zeros and every value of 1, you get the result as 1. So here 1 plus x is equals to 1 is being proved as tautology. I have already explained what is tautology. If the result is always true for every possible values, for any possible input, you are getting the result as 1, then that is we call as the tautology. In very first class of Boolean algebra, I told what is tautology. So here for every values of x, that is 0 and 1, the result is always 1. So this 1 plus x is equals to 1. This is being proved as a tautology for substituting all values of zeros and ones. Okay. Your third property is of zeros and ones is 0 into x is equals to 0. You have to prove that for every possible values of x, that is zeros and 1, you are going to substitute. You have to get the result as 0. So first you consider this as an LHS and this one is as an RHS. First time you are going to substitute the value of x, that is if x is equals to 0. Consider, you have to consider your LHS. What is the LHS? 0 into x equal to 0 into x. In place of x, you are going to substitute the value of 0. That is nothing but 0 into 0 is nothing but 0 according to your AND relation. We are going to use a relation that is nothing but AND. So this 0 into x is nothing but 0. Your RHS has been proved for the values of x. Similarly, you are going to substitute the value of x is equals to 1. Again consider your LHS. LHS is nothing but 0 into x. You are going to substitute the value of x. You are going to substitute the value of x, that is nothing but 1. So 0 into 1. Again 0 into 1 is nothing but 0 according to your AND relation. So your RHS is being proved. For every value of x, that is zeros and ones, you get the result as 0. This one we call it as fallacy. If you get for every possible substituting the values of a variable, either zeros and ones, you get the value always false or always 0. Such a condition we call it as fallacy. The truth table of this 0 into x is 0, x, 0 into x. 0 as it is, only the x value changes, 0, 1, that is nothing but 0, 0. So this is the result R. So for every possible values of zeros and 1, the result is always 0. For every possible value you are going to substitute zeros and 1, the result is always 0. Such a condition we call it as fallacy. Your third property is being proved. Okay. Your fourth property is 1 into x is equals to x. For every condition of x, that is zeros and ones, you have to get the result as the variable x. First condition, if x is equals to 0. You consider this is your LHS and this is your RHS. So you consider LHS, that is nothing but 1 into x. Substitute the value of 0 in place of x. That is 1 into 0 is nothing but, that is 1 into x is nothing but, you are going to place it as 0. 1 into 0 is again your, according to AND relation. According to AND relation it is 0. What is the value of x? 0 here it is nothing but x. So your RHS being proved. Next, for the condition of if x is equals to 1, consider your LHS. So LHS is nothing but 1 into x. In place of x, substitute the value of 1. 1 into 1 is nothing but 1 according to your AND relation. So 1, what it holds of? Again it holds of x. So your RHS is being proved. So the truth table of this particular property is first one, 1 into x. 1 into x is equals to x. So 1 as it is, 1 is x value 1. 1 into 0 is nothing but 0. 1 into 1 is nothing but 1. That holds the value of x. So your fourth property is being solved. So we have seen all four properties of the zeros and ones. So next is your laws. That is the first one is your idempotence law. What is this law statement? When a variable combined with itself using or and the output is the same variable. Once again I say, when a variable combined with itself using or and the output is the same variable. What this law states, when you consider any variable, when a variable combined with itself, you can use either or and operation. The output is the same variable. The result what you are getting when you are combining a variable with itself using your or operation, the result will be the same variable. When you are combining a variable with using an and operation, the result is the same variable. So consider if x is a variable, when used a or operation, when combined with itself, the result is x. You consider again x, this is the first condition. Second, a variable x, when using an and operation, you are combining with itself using an and operation, the result is the same variable, that is nothing but x. The logic gate of first one is x, the result r is nothing but x plus x is equals to x. We are getting the result as x. Next, for next second b, and logic gate is x r, that is nothing but x dot x. You should get the result as x. So we will substitute the values of zeros and ones and prove that x plus x is equals to x, x into x is equals to x. First condition will solve x plus x is equals to x. So this is your LHS and this is your RHS. So first you consider your LHS. So you have to prove that LHS is equals to RHS. Your LHS is x plus x is equals to. So first time if x is equals to 0. In first time you are going to substitute the value of x. Okay, that is equals to, so in place of x you are going to substitute the value of x, that is nothing but 0. So 0 plus 0 is nothing but your 0 according to your OR relation. According to your OR relation, I have already explained in your postulates. 0 plus 0 is nothing but 0. What is the 0 holds here? It is nothing but x. So x, that is RHS is the proof. First, substituting the value of x, that is equals to 0. Second, if x is equals to 1, consider your LHS. That is nothing but x plus x. So what's the value of x here? It is 1. For each place of x, you are going to substitute the value of 1. 1 plus 1, that is nothing but 1. According to your OR operation or OR relation. What is 1 again holds here, it is nothing but x. So x, that is nothing but your RHS is the proof. So the truth table for x plus x is equals to x is nothing but x. Okay, we are going to do x plus x is equals to x. First column represents the x value. So first time both 0, second time 0 and 1. For every, that is it, for every value of for first time both 0, second time 0 and 1. So here 0 into 1 is 1. That is nothing but your x is the root. In our idempotent law, the second b was nothing but a variable combined with itself using an AND operation. The result should be the same variable. First we have seen in A, the result that the variable combined with using a OR operation, the result is the same variable, that is x. So in B, that using an AND operation, how we are going to perform. So, you are going to substitute the value of if x is equals to 0. You consider this is your LHS, this is your RHS. So, consider your LHS. LHS is nothing but x dot x. So, in place of x, you are going to substitute it as 0. Okay, 0 into 0 is nothing but 0 according to your AND relation. According to AND relation, 0 into 0 is nothing but 0. The value is 0. What is this 0 holds here? Again, it is nothing but your x. So, RHS will prove. Next, consider if x is equals to 1. Consider your LHS. What is this LHS? That is nothing but x dot x. So, x dot x is nothing but 1 dot 1. So, you are going to substitute the value of x is nothing but 1. 1 dot 1. 1 dot 1 is nothing but 1 into 1. That is nothing but 1. According to your AND relation. According to your AND relation. So, that 1, what is this 1 into 1 is nothing but that 1 holds the value of x. Again, RHS is being proved. So, for every value of that is x is equals to 0, you are going to substitute the place of x 0. 0 into 0 is nothing but 0 according to AND relation. The 0 is nothing but again you come to x is equals to 0. The RHS is being proved. When you consider x is equals to 1, what is your LHS here? Again you are considering as x into x. In place of x you are going to substitute it as 1. 1 into 1 is nothing but 1. That is nothing but using your AND relation. So 1. What is that? 1 holds here is nothing but x. So your RHS will prove. The truth table for this x dot x is equals to x. So for both the value of 0 0, next 1 1. 0 into 0 is nothing but 0. 1 into 1 is nothing but 1. So this holds your x value and this holds your x value. So for every possible values of x into x, when it is combined using an OR operation or AND operation, the result is always the same variable. So that is about your idempotence law. Once again I am saying, idempotence law is nothing what it states means consider any variable when combined with itself using an AND operation or OR operation, the result is the same variable. Same variable. So we have solved now x plus x is equals to x. X into x is equals to x. So this law we have proved. The next law, the second law is involution law. What this law states means when I consider a variable, when it is complemented, again the complemented variable will get the same variable. What it tells means in involution law, a complemented variable is again complemented the result is the same variable. What it tells means a complemented variable is again complemented. What will get the result? The result is the same variable. In more understanding way, you consider a variable. A variable is complemented. So this becomes a complemented variable. When you consider a complemented variable, again you are performing a complementation. That is double times you are performing, twice you are performing a complementation. Then what will be the result? You will get the result as the same variable. That is nothing but your involution law. Once again I am telling, in involution law, what it tells means a complemented variable. A complemented variable is nothing but x bar. Is again complemented. You are complementing again the x bar. So the result what you are getting means the result is nothing but the original variable. That is nothing but the variable x. So that is the statement given by your involution law. Involution law is nothing but a complemented variable is again complemented. The result is the same variable. This law is also called as double inversion law. This law is also called as double inversion rule of law. This law is also called as inversion rule. Why? Means you have 2 times you are performing the complementation. Twice you are doing the complementation. So it is called as the double inversion rule. So the what is the logic gate of this is nothing but, so consider variable x bar. Okay, when it goes here, that is nothing but x double bar. The result will be your x. So this is the logic gate. What is this logic gate? Means you are considering your one NOT gate, again the NOT gate. 2 times you are complementing, so 2 NOT gate. When you consider variable x, when it is passes through your NOT gate, it becomes a complement then. Again, when it passes through another NOT gate, it becomes twice the complement. Then the coming output signal, what it comes is, it comes your original variable, that is nothing but the x. For example, you consider 0. X is 0. When it passes through one NOT gate, it becomes 1. When it passes through another NOT gate, it becomes 0. That is nothing but your original value of x. So when you consider 1, when you consider 1, when it passes through, when you consider x, when it complemented, it becomes, when it passes through one NOT gate, it becomes 0. When it passes through another NOT gate, it becomes 1. That is nothing but your original value x. So you consider a truth table x bar, x double bar. That is nothing but x. So 0, NOT gate, that is nothing but inversion rule. It takes only one value. At a time, it takes only one variable. That is nothing but your inversion rule. So 1, consider one variable, that is nothing but x. So x bar is nothing but 1. So twice you are doing, that is nothing but 0. That is nothing but your original variable x. When you consider x is equals to 1, the complement of it is 0. Again, if you double times you complement, that becomes 1. That is the original value x. Solution law. Once again, I am telling you, see here, involution, very important law. Involution law is nothing but, comes for 2 marks or 3 marks. Involution law is nothing but, a complemented variable is again complemented, you get the same variable. Twice you complement a variable, you will get the original value. In other terms, I can tell, a variable is twice it has been complemented, so you are going to get the original value. This law, in one mark question, what is it? Which law is called as involution law? Law is called as, you can say double inversion rule, or double inversion rule is also called as involution law. So they can question us, both the laws are, involution law is also same as double inversion rule also same. If they ask the question, explain double inversion rule, you can go and explain involution law. One and the same. The involution law is also called as the double inversion rule. Why? Next, twice you are complementing the variable. So this is the logic circuit of or logic gate of your double inversion rule. That is twice you are using a NOT gate, and the truth table of this particular double inversion rule is nothing but this one. So this law completes the third law. So the third law is complementarity law. Of this law states a variable combined with its complement. When a variable combined with its complement using an AND or what will be the output? First we consider a variable combining with its okay, with its complement, you get the result as always 1. What it tells means a variable with its complement using an OR operation, the result is always 1. How we are going to prove it? Using substituting the values of zeros and ones. First time, if x is equal to 0, consider your this is as your LHS and this one is your RHS. So the logic circuit or the logic gate of this is of expression. Okay, x. You take your OR operator, that is nothing but x bar. That is nothing but x plus x bar is always 1. This is your logic diagram or logic circuits of the first condition under the complementarity law. What it is, consider variable x. So first input, the one input combined with its complement variable x bar, the result is always 1. How we are going to prove is nothing but, first time you consider x is equals to 0. This is your LHS and this is your RHS. Consider In place of x, you are going to substitute the value of 0. So 0. Next x 0 0 bar. That is nothing but 0 plus 0 bar becomes 1. 0 plus 1 is nothing but 1 according to your OR relation. According to your OR relation. So 0 plus 1 is nothing but 1. So your RHS has been proved for the value of x is equals to 0. Next, consider if x is equals to 1, consider your LHS. Your LHS, that is nothing but x plus x bar. In place of x, you are going to substitute the value of x, that is nothing but 1. 1 plus 1 bar. 1 as it is, 1 bar is nothing but 1 of not operator will be 0. 1 becomes 0. So 1 plus 0 is nothing but 1 according to your OR relation. According to your OR relation. So 1 plus 0 is nothing but 1. So what we want holds here is nothing but your RHS is being proved. That is x plus x bar is equals to 1. So again your RHS is being proved. For both the values of x is equals to 0, x is equals to 1, when you complement with its variable, so the result using an OR operation, the result is always 1. The truth table for it is x bar, x plus x bar. Okay, first time 0, second time 1. So 0 complement becomes 1, 1 complement becomes 0. 0 into 1 is 0 plus 1 is 1, 1 into 1 plus 0 is 1. So both the way the result has been proved as 1. For every value of x either 0 or 1, the result is always 1 with the help of complementarity law. So this x plus x bar is equals to 1 is we call it as tautology. Tautology. So what it is, for every value of x either 0 or 1, in a complementarity law using an OR operation, the result produces always 1 or 2. Such a thing we call it as the tautology. So this first law under the complementary law is being proved. Second one, second rule or second law under complementarity law is nothing but we are using an AND operation. We are taking a variable, making a complement of its variable, and the result what it is produced is nothing but always 0. That for every value of, we are going to prove that for every value of x, substituting the values of x, that is 0s and 1, we are going to prove that LHS is equals to RHS. The logic diagram or logic circuits of this particular rule is x is the variable, the complementary, that is nothing but using a NOT gate. Both when it is using AND operation, the result is 0, or R which holds the value x into x bar is equals to 0. So first time x into x bar, you consider this is your LHS and this is your RHS. I am considering LHS. If x is equals to 0. So in place of x, I am going to substituting 0, 0 dot 0 bar. So 0 as it is, 0 bar is nothing but my 1, complement of 0 is nothing but 1, 0 into 1 is nothing but 0, that is according to your AND operation. Okay, according to your AND operation. So that is nothing but your RHS has been proved. Next, consider for x, if x is equals to 1, consider your LHS. That is x dot x bar. In place of x, you are going to substitute the value 1. 1 into 1 bar. 1 as it is, 1 complement becomes 0. 1 into 0 is nothing but 0. According to your AND relation. Okay. So 0 is nothing but your RHS. RHS has been proved. The truth table for this is x as it is, x bar, x dot x bar, that is equal to 0. For 0 bar, x complement becomes 1 0. 0 into 1 is 0. 1 into 0 is 0. For every value of 0, substituting the value of 0 and 1 in a complementary rule using an AND operation, the result is always 0. That is x dot x bar is equals to 0 means for every value of 0, either this can be 0 or for every value of x, it can be 0 or it can be 1. The value is always 0. That is we call as the fallacy. Once again I am telling you, see, complementarity rule, under first rule using an OR operation we have done, second rule using an AND operation. In the AND operation we are going to take a variable, make a complement of that variable, and using a AND operation that you have to prove that it is always 0. So I am considering first case it is nothing but 0. I am substituting the value of x is 0. In place of x I am substituting 0. The complement is being changed and I proved it is equal to RHS. Next condition for x is equals to 1. I am considering my LHS, substituting the place of x is equals to 1. 1 into 1 bar, that is nothing but 1 into bar. 1 complement becomes 0. 1 into 0 is nothing but 0. According to your AND relation, your RHS is being proved. The truth table between your x into x bar is nothing but for x you are changing the value of 0 and 1. X bar, take the complement of 0 is 1. 1 complement becomes 0. X into x bar is equals to 0. We both the substituting value get the result as 0. So this we call it as fallacy. So the complementarity law is being proved under two conditions. Okay. Fourth law is commutative law. In this law, we are going to prove that you are already studying in your school days commutative law, associative law. Again, you are going to study in your Boolean algebra how this law is being used in your logic circuits. In this law, two conditions are there using an OR operation as well as the AND operation. You have to prove that x plus y is equals to y plus x. Second one, x into y is equals to y into x. You have to prove the law that x plus y is equals to y plus x. X into y is equals to y into x. So we will see the logic circuits of both the things and then one by one we will solve the problems. First one, the logic circuit. You are going to come using an OR operation. X plus y. The result is nothing but r, that is the x plus y. Okay, this should be equal to y plus x. Y plus x. This first logic circuit of your first condition. Second, using an AND gate, x, y. That is your r, x into y. This should be equal to y into x. R specify the output or result. So first condition we will see. So first condition, you have to prove x plus y, your LHS is equals to y plus x. You are going to substitute the values of x is equals to 0 and you are going to x is equals to 0. You are going to substitute the value 0 and 1. You are going to prove that x plus y is equals to y plus x. So this is your LHS and this is your RHS. So first we consider if x is equals to 0. So you consider your LHS, consider your LHS. What's my LHS here? It is x plus y. Okay. Now consider your LHS, x plus y. What is this? X plus y is nothing but 0 plus y. 0 plus y. So in place of x I am going to substituting x is equals to 0. 0 plus y, that is your properties, first property, 0 plus x is equals to x. In place of x, here it is given as y. 0 plus y is nothing but again y. This is for LHS the output. Consider your RHS. RHS. You consider your RHS, that is y plus x. Now, if x is equals to 0, you are going to substitute the value of 0. So here y plus x, that is nothing y as it is. In place of x, you are going to substituting 0. Again the condition of properties of zeros and 1. 0 plus x is equals to 1. In place of x, they used a variable y. So y plus 0 is nothing but again y. So here LHS is equal to your RHS. The first condition is being solved. Okay. Okay, next term, first we have seen x is equals to 0. Next we are going to see if x is equals to 1. You consider your LHS. Consider LHS. So they consider your LHS, that is nothing but x plus y. So x plus y is nothing but in place of x you are going to substitute 1. 1 plus y. So 1 plus y, again go for properties, that is 1 plus x is equals to your x. So 1 plus x is equals to 1. 1 plus x is equals to 1. Your properties, 1 plus x is equals to 1. Here 1 plus y, in place of x it is the y. So 1 plus y is nothing but again 1. Okay. Now consider RHS. Consider your RHS. In RHS, y plus x. So if x is equals to 1, y plus 1. Y plus 1, again it is nothing but 1 plus x is equals to 1. In place of x, there is y. Y plus 1 is nothing but your 1. So your LHS is equal to your RHS. So your LHS is equals to your RHS. So for every possible values of x, either zeros and 1, your x plus y is equals to y plus x. That is LHS is being proved to RHS. The truth table of this is x, y. X plus y, y plus x. 0, 0, times 0, 1, 1, 0, 1, 1. X plus y. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 1. Next, y plus x. 0 plus 0 is 0. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 is 1. So, this x plus y is equals to y plus x. X plus y is what's the value? 0, 1, 1, 1. Y plus x is equals to 0, 1, 1, 1. So, for every possible values of LHS is equals to your RHS. If you substitute the x value either in 0, you get the same value as it is in your RHS. If you substitute x is equals to 1, consider x is equals to 1. Then also if you substitute, the LHS is being proved to your RHS. So commutative law is being proved under your Boolean theorems using your Boolean algebra with the help of the properties of zeros and ones. Okay. See your commutative law, the B part is using an AND operator. You are going to prove that LHS should be equal to your RHS. So first we have seen your OR condition. Now next we see your AND operation. We have seen your logic circuit. So this is your LHS. You have to prove that all the values in the LHS should be equal to the RHS for all the possible values of zeros and ones. First time, if x is equals to 0, consider LHS. So what it is LHS? Equal to x dot y. X dot y. So in place of x, you are going to substitute it as 0. And under commutative law, the second rule is using an AND operator, you are going to prove that x into y is equals to y into x. You have to prove that LHS is equals to your RHS. So, first time you are going to use the condition x is equals to 0. First time you have to substitute both the values, that is x is 0 as well as the 1. So, x is equals to 0. Consider your LHS. What is this LHS? It is nothing but x dot y. So, I am going to substitute the value of x, that is nothing but 0. 0 into y. So, under the property, third property, what it is? 0 into x is equals to 0. In place of x, here it is y. So, 0 into x is nothing but 0. 0 into y is nothing but 0. This is the value of LHS. Now, consider if x is equals to 0, consider your RHS. Consider your RHS. What is RHS here? It is y dot x. Here y as it is, the x value changes to 0. Y into 0, that is 0 into x, that is nothing but 0. So the value is 0. So your LHS is equals to your RHS. So the first condition for value LHS is equals to your RHS. So next condition is, first thing we have substituted x is equals to 0. Next thing we are going to substitute x is equals to 1. So consider the LHS x dot y. So 1 dot y. That is nothing but 1 dot x is equals to, fourth property I am using, 1 dot x is equals to x. So 1 dot y is equals to y. So this is for your LHS. Now consider your RHS. Consider your RHS, that is y dot x. So you consider RHS y dot x if x is equals to 1. Y dot x is nothing but your 1. That is the same condition. 1 dot x is nothing but y dot 1. In place of x, it is y. Again, it is nothing but your x. That is nothing but your y. So your LHS is being proved to your RHS. Okay. So here in a second condition, using, that is in your commutative law, that is your second part, x dot y is equals to y dot x. That is, I am using an AND operation. First thing we solved using x is equals to 0. Second thing we have solved x is equals to 1. The truth table of this particular AND operation is, AND operation is x dot y, y dot x. Okay, 0 0 0 1 1 0 1 1. You have to do a AND operation. 0 into 0 is 0. 0 into 1 is 0. 1 into 0 is 0. 1 into 1 is 1. Next, you are going to do a y into x. That is 0 into 0 is 0. 1 into 0 is 0. 0 into 1 is 0. 1 into 1 is 1. So, the commutative law, what it tells means x plus y is equals to y plus x. X into y is equals to y into x. For both the value, that is x plus y is equals to y plus x. X into y is equals to y into x. We have solved substituting all the possible values of zeros and ones in your OR operation as well as your zeros and ones in your AND operation. Both the condition, your LHS is equals to your RHS. So this is about your commutative law. The next law is associative law. In this law, what it tells means x plus y plus z. You are considering three variables. X plus y plus, that is associative. This grouping y plus z is plus x is equals to x plus y in the bracket plus z is equals to. We should prove that this particular LHS should be equal to the RHS. So the logic diagram or circuit of this particular associative law. First I am taking y plus z, the bracket, the innermost y plus z. I am going to using an OR logic gate and getting the output as y plus z. That should be again OR with an x input. Then the result whatever you are getting, that should be equal to x plus y OR gate along with your z OR gate. So you have to prove this. X plus y plus z is equals to x plus y in the bracket plus z. This condition should be solved under your associative law. For this, first we will consider, this will be your LHS and this is your RHS. Consider your LHS. So consider your LHS, that is x plus y plus z. Okay, you are going to consider x plus y plus z, that is nothing but your LHS. You are going to substitute the value of if x is equals to 0. In place of x, you are going to substitute it as 0. That is nothing but 0 plus y plus z. Again use the property 0 plus x is equals to x. So 0 here x what it holds, that is nothing but y plus z. That is y plus z. So this is for your LHS. Now consider your RHS. Consider your RHS. What it tells means x plus y plus z. If x is equals to 0, that is nothing but x place, you are placing 0 plus y plus z. So again use the 0 plus x. Here 0 plus x 0. What it holds means 0 is nothing but this particular 0 plus y, that is nothing but in place of x it holds y. That is y plus z. So your LHS is being proved for your RHS. LHS is being proved to your RHS by substituting the value of x is equals to 0. Next we will consider substituting the value of x is equals to 1. Okay. So next we have solved for x, substituting the value of x is equals to 0. Now we will substitute the value of x is equals to 1. So if x is equals to 1, so consider your LHS as it is 1 plus y plus z. That is nothing but, that is what it tells means 1 plus x is equals to 1. 1 plus x is equals to 1. What it tells means 1 plus y plus z is nothing but 1. So this condition takes the value of x. So you have done for your substituting value of x is equal to 1 in your LHS. Substituting the value of x is equals to 1, you have to substitute in your RHS. Consider RHS. What is RHS? X plus y plus z. Substitute the value of x, that is 1 plus y plus z. This holds the property 1 plus x is equals to 1. So here 1 plus x is nothing but this holds the 1 plus x. That is nothing but 1. See here what I am telling is 1 plus y holds the value of 1 plus z holds the value of x. So 1 plus x is equals to 1. So here LHS is equals to your RHS. Once again I am explaining. See, understood? For first condition we have substituted x is equals to 0. In that condition we solved LHS is equals to your RHS. Now next condition you are going to substitute x is equals to 1. In this I am considering LHS x plus y plus z. In this x is equals to 1. Here what it tells means in place of x you substitute 1. Y plus z as it is. You go for the properties of zeros and ones. This is the form of 1 plus x is equals to 1. X holds the, what it stands for x here it is y plus z. Consider y plus z as x. 1 plus x is equals to 1. So 1. So this is for your LHS. Second time you can substitute for your RHS. RHS when you substitute if x is equals to 1. So in place of x you are going to substituting 1 plus y as it is plus z as it is. 1 plus y, this holds nothing but 1 plus y is nothing but I have already told it holds the value of x and z holds the value of 1. So x plus 1 is nothing but your 1, that is nothing but your RHS. The truth table of the associative law is x, y, z as a 3 input and we have partitioned into how we are going to consider under the bracket the associativity y plus z, x plus y, x plus y. Separately we are going to do an OR operation on these two, both the things. So to consider your input 1, 2, 4, I have already explained how to partition of 3 input. So 0, 1, 2, 3, 4, 5, 6, 7. So first time 0, everything is 0. Next time 1. In place of 1, place it is 1, other thing 0. This is nothing but a 2's multiple. 1 2's are 2, 2 2's are 4. Next 2, 0, 1, 0. 3, 2 plus 1 is nothing but 3, 0, 1, 1. 4, in place of 4, place it 1, the remaining place is 0. 5, 4 plus 1 is 5, 4 plus 1 is 5. 6, 4 plus 2 is 6, 4 plus 2 is 6, 0. 7, 4 plus 2 plus 1 is 7, 4 plus 2 plus 1 is 7. Next, in associative law, first thing the innermost, that is y plus z, that one we saw. Next, we are going to do that x plus yz, the bracket is equals to x plus y, the bracket plus z. So you do a OR addition, y plus z. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 1 plus 1 is 1. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 1. We have done y plus z, the OR addition. Next we will see x plus y, the OR addition. 0 plus 0 is 0. 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 1 is 1. 1 plus 1 is 1. Now, so you got y plus z, x plus y. So you do with this particular thing, you do OR addition with your x. Y plus z should be done an OR addition with your x. So these two first time, these two. Okay, 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 1. 1 plus 1 is 1. 1 plus 1 is 1. So once again I am telling, you do your x or with your x plus, y plus z. You are going to do, you need an associative, that is your LHS should be proved to your RHS. So you do a OR addition with x with y plus z. 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 1. 1 plus 1 is 1. 1 plus 1 is 1. So first LHS we have solved. Now we go to RHS. What it tells means, take your x plus y, that should be OR with your z. These two. So 0 plus 0 is 0. 1 plus 0 is 0. 0 plus 0 is 0. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 is 1. 0 plus 1 is 1. 1 plus 1 is 1. 0 plus 1 is 1. 1 plus 1 is 1. See here, once again telling, you are going to take this particular x plus y should be OR with your z. That is these two. 0 plus 0 is 0. Okay, x plus y, that is here. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 1. So, you consider your LHS and RHS, both the values be same. So, the associative of x plus y plus z equal to x plus y plus z. We have proved under the condition using your OR statement for every value of 0 as well as each value of y. X is equals to 0 as well as x is equals to 1. So this ends your associative law. Okay, the next law is your distributive law. What this law states means, x into y plus z is equals to xy, the multiplication x into y plus x into z. You have to prove that your LHS is equals to your RHS for substituting the values of zeros and ones. So the logic diagram for this or circuit diagram for this is, you can consider your y plus z using a OR gate. Okay, OR gate that should be AND with your x. The whatever the result R it is being produced, that should be equal to your xy plus xz. xy using your AND gate. xz you are using your AND gate. Okay, the result x into y, the result whatever you are going to get xy, and the result x into z using an AND gate is xz. These two should be OR using your OR gate. The result, whatever the result outcome it should be, has been come, that should be equal to the result which has been produced in your LHS. This is the logic circuit. What it explains means, the LHS circuit should be, the value should be, result should be equal to your RHS result. So we will prove. Okay, consider your LHS. What is my LHS? X into y plus z. Okay, this is my LHS. If x is equals to 0. Okay, you are going to substitute the values of x is equals to 0. That is what it tells me. In place of x, you are going to substitute it as 0 equal to 0 y plus z. This is in the form of property. Okay, that is 0 into x is nothing but 0. So here 0 into x is nothing but here 0, the properties of 3 zeros and ones 0. So this is for your LHS. Now you go for your RHS. Consider your RHS, that is nothing but x plus y plus x into y plus x into z. So if x is equals to 0. So in place of x, you are going to substitute 0. 0 into y plus 0 into z. That is nothing but 0 plus 0. You are going to get the result as 0. This is for your LHS is equals to your RHS for substituting the values of x is equals to 0. So when you substitute x is equals to 0, your LHS getting the result as 0. When you substitute x is equals to 0 in your RHS, you get the value as 0. Both the condition LHS is being equal to your RHS. Next, if x is equals to 1, you consider your LHS. What is my LHS? X into y plus z. In place of x, you are going to substituting as a 1. So